Hello everyone, and thank you very much for joining this session at the CloudGen 2021 conference. We are going to talk about how to operate Kubernetes workloads using one of the mostly used patterns in Kubernetes, which is the operator pattern. First of all, thank you very much to the sponsors, to the partners, which allows to have this conference today. So thank you very much, everyone. And let me say that if you want to tweet about this session, you want to talk about this conference, you can use this tweet handle or the hashtag CodeGen2021. So let me introduce a little bit about myself. I am Paolo Patierno. I am a principal software engineer in Red Hat on the messaging and data streaming team. I am maintainer of one of the projects that I'm going to talk about a little bit during the demo, just as an example of what I'm going to show during this session. So I am maintainer and committer for this project, and other than this for other projects in the Eclipse Foundation. I am also Microsoft MVP in the Azure category. As you can see, I love a lot the sports, kind of Formula One, MotoGP, and even football. So let's move on and talk about Kubernetes. So let's start with Kubernetes because this session will be focused on Kubernetes and how it works somehow. So we can think about Kubernetes as a kind of Linux kernel for distributed systems. So what I mean is that you have your cluster that can be made by bare metals or even virtual machines, and you install your Kubernetes on top of it, your Kubernetes platform on top of it, and Kubernetes is able to kind of add a abstraction layer on top of the hardware that you have, so that you can write your application, you have containerized your application, and you can move your workload across different Kubernetes platform, running on different nodes, and everything should work fine. Kubernetes helps you to automating the deployment of your application, the scaling, the management, and so on. So what are the main features that we have in Kubernetes today? First of all, the container scheduling. So you create your application, you containerize your application, your containers are grouped into pods, which is the kind of unit of work in Kubernetes, and then Kubernetes schedule the execution of your containers, of your pods on the nodes that made your cluster. It provides the self-healing, so if your application is crashing, Kubernetes will detect that using some probes and then will restart your application without having you to act manually on the cluster to do that. It provides a way for scaling the application and doing load balancing. So if you have more replicas of your application, it's able to scale this application up and down with more and less replicas, but even balancing the traffic across all the replicas. Provides you a way for enabling storage, so for application where you need for storing data permanently, or for handling configuration your application, or even with secrets about TLS certificates and so on. Last but not least, even allows batch executions and automation for rollout and rollback. If you want to upgrade your application to a new version, or you want to do a kind of rollback to the previous version if something goes wrong. So talking about Kubernetes workloads, in the end, we can say that you see in Kubernetes pods everywhere. As I already said, your application is containerized, and Kubernetes runs these containers inside pods. So you can have one pod made by one or more containers. It depends if your containers, your applications inside these containers has to be tied together for some reasons related to the business logic that they run, or you can split them across different pods. But in the end, the pod is the unit of work in Kubernetes. So what you do is you describe the pod, the Kubernetes native resource, which is the pod, with information about the image of the container that you want to run, and then you run your application. So this is in the end what makes the workloads in Kubernetes. But I listed a lot of cool features that we have in Kubernetes. But how really Kubernetes handle things like scaling, rollout, batch execution, and so on, without having the human intervention somehow? So let's see the trick, more or less. First of all, don't use the pods. So don't write your own pod for describing your application, asking to Kubernetes to execute that pod, the application in that pod, but let's use something which is more sophisticated. I'm pretty sure that all the people right now, all the developers don't use pods in the end, but use replica sets or deployment. So a replica set is a Kubernetes native resource that guarantees a specific number of replicas. So you specify in your YAML describing your replica set that you want, I don't know, 3, 5 or more replicas of your application, and replica set and Kubernetes using this replica set will guarantee that there are a number of pods has the number of replicas that you asked for. So in this way, new pods are spinned up, or they are killed if they are too much when you describe your replica set. This is based on the so-called selector, where in the replica set you define kind of I want to run these pods having this kind of labels, but we will see soon an examples for that. The other one is a deployment. A deployment is based on a replica set. So when you create a deployment resource in Kubernetes, you have a corresponding replica set for spinning the replicas, so your pods, but it adds an extra layer for doing rollout and rollback. So for upgrading your applications to a new version, or doing a rollback if something goes wrong and you want to roll back to the previous version. These are not just the only ones sophisticated things or objects that you have in Kubernetes, but there are more. Like, for example, stateful sets. If you are running a stateful application and you need kind of unique identities for your pods, while in general you use deployment and replica set for stateless applications. There are also jobs like the cron job for running some job periodically, or even daemon set for running some application as a daemon on all the nodes in your Kubernetes platform. So don't use the pod, use some more sophisticated Kubernetes native objects resources that we have in order to run your workload on Kubernetes itself. But how really does Kubernetes do the trick? So we have these special resources, but what's behind these special resources for behaving in this way? There is the concept of a controller. So the controller in the end is another application running on Kubernetes, which tracks the Kubernetes resource that you deploy on Kubernetes itself. So it makes sure that what you describe in your Kubernetes resource, so the so-called specification in the spec field of your Kubernetes resource, matches the state of that resource on the cluster. So the application is running, I want to use this amount of memory, of CPUs, I want to expose these ports and things like that. So it's controlling actively that what you describe in the specification is exactly the state that is running on the cluster. Of course, it does that interacting with the API server, so the Kubernetes API server that we'll see in the next slide, and it acts as a control loop. So there is a control loop where the controller running continuously check the specification and check that it matches with the state that you want in your cluster, right? So because so for working the replica sets, the deployments, and all the other stuff that I mentioned in the previous slide, there are some built-in controllers in Kubernetes. For replica set controller, the deployment controller, so there is a component in Kubernetes which is called the controller manager that inside runs these built-in controllers. So let's take a quick look at this. We know that the control plane in Kubernetes is made by 4 main components. The first one is the API server. So the API server is really an HTTP server, which is the only one that your applications, so you from the command line when you want to deploy something on Kubernetes, or the controllers or your application can interact with. So the API server exposed all the Kubernetes resource, all the Kubernetes objects in a REST way, in an HTTP REST way, right? And all these objects in Kubernetes are stored in an etcd database, which is not accessible just through the API server, so everything goes through the API server, as well as there is the scheduler. The scheduler is the component that is in charge to find the node where you can run your pod, your container, when you are asked for it. So you ask through a replica set, through a deployment, or even just through a pod resource to run your container. It will be the scheduler to find the right node for scheduling that application running on that node, even based on some criteria like the available memory or CPUs and things like that. The other main components in the control plane is, as I already mentioned, the control manager, where the controllers for all these built-in special resources runs. So the controller, as I already explained before, acts as a loop that we'll see in a bit. But what's doing? It's kind of watching resource in the API server. So for example, the replica set controller is watching for the creation of a replica set. So if you from the command line create a new replica set Kubernetes object with your YAML, so it's created through the API server, it's stored in the etcd. The replica set controller is watching that the new replica set was created, and at that point it makes everything happen. So creates the pods as the number of replicas that you are asking for. So it's acting through the API server with a create operation to create actually the pods resources, and then the scheduler will take care of it in order to find the right node for scheduling your application in these pods. So there are some main operations: the watching, the create and patch for editing and changing a replica set, for example, in this case, so increasing or decreasing the number of replicas and so on, or even getting the status, listing the resources, etc. So this is how all the pieces in Kubernetes interact with the API server, and how a controller is able to control a specific Kubernetes built-in resource in order to make everything working. So let's move on and talking a little bit about the controller loop. As I already mentioned, a controller works in a kind of loop. So what it does on the right hand side, you can see the first operation is about observe. So it's watching, is observing through the API server, to the watch operation, what's happening on replica set resources. If a replica set is created, or even if a replica set is updated, so its specification is changed because the user did that, right? So when something happened after the observation of the resource, the corresponding controller analyzes, so and check if what you describe in your spec is actually what you want to be running on the Kubernetes cluster, so reflecting the current state on the cluster. If that's okay, there is no actions to take. If it's not okay, it will make some changes. So they will need to make some change on the cluster in order to have the state of your application matching what you are describing in your resource. And this loop just runs forever. So your controller is an application running this kind of for endless loop of observe, analyze, and act. Let's make an example. So just talking and keep talking about how the replica set controller work. So on left-hand side, you can see a replica set definition. So I have my replica set with a name. I am specifying that I want 3 replicas. I have the template section. The template section is just the template of the pod that will be created by the replica set controller. So I am just describing how these pods will be. So I am specifying what is the image, in this case, the labels that I want to apply. And the replica set has also a selector. So it means that this replica set resource will take care somehow of all the pods that have a labels as app equals to my app. So if you have pods with this label, the replica set will take care of them. If you have pods with a different label, so that don't match this selector, then these pods will be, I don't know, pods created alone or will be handled by a different replica set, but not this one, because they don't have this specific label, which is about app, my app. Say that what happens when you create this replica set resource, the replica set controller will create the 3 corresponding pods on the right hand side. So the name of the replica set dash a kind of random ID. This is what happens. So it will create these 3 pods. Next, let's try to create 2 pods this time with the label matching the selector in my replica sets. So what I'm going to try is to say I don't want 3 replicas of my application, but I want 5. On the right hand side, you can see that at some point the pods are created but then destroyed, because the replica set controller will see that there are now 5 pods matching the labels, while you are asking for 3 replicas. So the new created pods will be just deleted somehow. So the replica set controller guarantees that only, in this case, 3 replicas will run, because you are asking for 3 replicas. It creates 3 replicas. If you try to move forward in this way, having more replicas, you don't have that. It means that the only way to scale in the replica set will be increasing the replicas field. So on this slide, on the previous slide, you can change this field, replicas, from 3 to 5. The replica set controller will see that the spec doesn't match the status because I don't have 5 pods, but I have just 3 pods running, and it will add 2 more pods in order to match what you are asking for. Let's do the other way around. Let's say that I have no replica set yet. I create just these 2 pods with the same label, app, my app. The 2 pods are created. There is no replica set right now. Then I create a replica set. A replica set with the same specification as before. 3 replicas that match labels and so on. What happens is that the replica set controller will see that 2 pods with that label already exists from a creation of the previous pods resources. So in order to reach the status, which is having 3 replicas, it has to create just 1. So this is how it will behave. It's not going to create more 3 replicas, but just 1 for reaching the 3 matching that selector labels for having the 3 replicas that you want. It means that if at some point you delete these 2 pods resources, the replica set controller will create 2 more pods here for matching your request about 3 replicas. So this is how a replica set controller works somehow. It's just in this loop checking the replica set specification and checking that it matches what you are asking for, the number of replicas or even other criteria that you are specifying in your spec. But we know that with Kubernetes and with containers, the humans build complex applications, so using these bricks. And when you create your application, your business logic, the human, so the developer in this case, knows about the complexity of the application, how it behaves internally, how to deploy it, how to upgrade it, how to react to bugs, issues, how to react to configuration change, to security changes, and things like that. And it's everything related to your specific application. So right now there is no Kubernetes in the picture, right? But what if we want to automate somehow operating this application? So the way that Kubernetes is able to operate replica sets, deployments, so is able to guarantees that I have the number of replicas that I want running, I have that configuration, etc., etc. I can handle that kind of upgrade or rollback if something is wrong. Is that possible doing something like that for our applications? There is a pattern, the so-called operator pattern, which was introduced by a company named CoreOS in the past that was then acquired by Red Hat, which is the one that you can use for that. So this is the one that we are going to explore in the next slides. So what is an operator? First of all, an operator is a containerized application. So it's another application running on your Kubernetes cluster. So instead of having a human taking care of an application, you have a kind of robot, an operator takes care of your application. But it has the knowledge of a specific business domain. So it means that as the developer knows how your application behaves, this knowledge has to be transferred into the operator. So when you develop your operator, you have to transfer the knowledge about your business application into the operator. The operator is able to manage the application lifecycle, so the deployment, the upgrades, configuration changes, and things like that. And it leverages a kind of extension point in the API server, which is called the custom resource definition. So as in Kubernetes, we have a native resource, replica set, pods, deployments, config map, secrets, and things like that, which are native Kubernetes objects. You can extend and create your own custom resource. I will show what does it mean in a few. The operator takes care of one or more of this custom resource. And what has inside? One controller for each resource. So it comes to the controller now. So you have an operator, which is a kind of CRDs plus controllers. And each controller inside an operator is just taking care of a specific custom resource, as the replica set controller takes care of a replica set resource. So what the operator does in the end, when you create your custom resource in Kubernetes, it will create for you some native Kubernetes resources, the so-called operands, leveraging, so using the built-in controller. So it means that if you have your custom resource describing your application and you give that to your operator, it in the end has to deploy something. So it will create, for example, the replica sets for running your application. It will create the config map for you for configuring your application, the service for making your application discoverable from other applications, and so on. So instead of having the human creating all these things, it's the operator starting from a unique custom resource. So from a Kubernetes point of view, what I was saying is that you can see here the CRD, the extension point. So you create your custom resource definition, so a definition that describes your custom resource. We will see an example. And in the end, you, from the command line, you create your custom resource as you create a replica set, but it will have another name, depends on your application that you are creating here. And your controller inside the operator will watch for that, will create corresponding operands. So deployment of your application, as already mentioned, config map, secrets, or even PVC for storing data, and so on. So it's the same kind of picture that we saw before about the built-in controllers. But right now we are not talking about built-in controllers. We are talking about custom controllers. So controllers inside operator that are able to handle a specific application. It's not needed that a controller from your custom resource creates operands like Kubernetes built-in resource, but it could even interact with external service. As we see, it could be an Azure service, an Amazon service. So you describe through a custom resource an Azure service, and then a corresponding controller will do something, some operation contacting this external service, doing some operation and returning back some results. So it's not just about creating operands as Kubernetes native resource, but it could be even communicating with an external service. So let's see an example. This example on the right hand side that I will show at the end of this session as a demo is coming from the project that I work on, is the StreamZ project that provides a way for running Kafka on a Kubernetes cluster. So it means that if you want to run Apache Kafka, which is a stateful application on a Kubernetes cluster, one way you have is as a human describing your stateful set, creating manually your config map with configuration secrets with, I don't know, TLS certificates, PVCs for storage. So you can do that, but it's really complex, right? It's simpler if you can describe your Kafka cluster just in one place, and then the operator will take care of creating for you all the Kubernetes native resource behind your custom resource. So what you do with a custom resource definition, a custom resource definition is again a Kubernetes resource. In this example, I am creating a new custom resource, which the kind is Kafka. And I am describing through an API schema what is the spec, what is the status of this Kafka custom resource. So I am creating a new Kubernetes resource, which is a custom resource, and it's named Kafka. From this custom resource definition, where I add a so-called extension point in the API server, so an API server is now able to recognize that there is a new resource, so there is a new endpoint, so an application can ask for Kafka list, can ask for a specific Kafka custom resource, as we ask for pods for replica sets. On the other side, you can create your custom resource. So other than describe the custom resource definition, then I am going to create a Kafka resource. So as I have a kind pod, kind deployment, now I can create my resource as kind Kafka. This is the specification in this case. I am describing which version of Kafka I want, the number of brokers, the listeners for exposing Kafka outside or inside my clusters, the configuration of the brokers, the kind of storage that I want to use, and right now even Zookeeper that runs alongside Kafka. But it will be removed so soon, as you know. And then the status, where the controller will report the status of the Kafka deployment, Kafka installation. So the controller inside the operator will take care, will watch this Kafka custom resource, and will create everything on the right-hand side. So we need stateful set for having Zookeeper running, Kafka running. We need config map and secret for configuration, TLS certificates, and so on. We need PVC for storing the messages in Kafka. We need the network policy for kind of security, so having these Kafka nodes made accessible on specific listeners just from the other Kafka brokers, and so on. So this is what the controller is doing for me. Instead of having me writing all the things that I have on right-hand side and handling by hand all this for upgrades, I can just write this Kafka custom resource, and the controller will do the rest. So in the end, an operator, as already mentioned, a controller, an internal controller, one or more internal controller watching the corresponding custom resource, like the Kafka custom resource, and it will create, update, delete all the operands. That could be native resource, but even external service. And it could be even other custom resource. So if I have another operator, so the first operator will create a custom resource watched by another operator. But it also does the work in the other way around. It watches the operands. So if the controller creates the stateful set, config map, and so on, and someone tries manually to change the config map or the stateful set directly, it will reverse back the changes, because the controller has the role to watch the Kafka, the custom resource, the Kafka resource in this case, and matching with what we have in the stateful set, in the config map, and so on. If something is changed manually in these operands, the changes are reversed back because they don't match what we want in the custom resource definition, right? In the Kafka resource in this example. Of course, it depends on the logic that you want to have, but in general, this is how the operands behaves. And all these resources are owned by, so they have as an owner, which is a kind of reference in a Kubernetes resource, the custom resource. So it means that we can leverage the Kubernetes garbage collection. If I delete the custom resource, all the corresponding operands, Kubernetes native resource, will be deleted. As I mentioned, it's not just about operands as Kubernetes resource, but they can be even external service, like, for example, an Azure service operator, where it watches for a custom resource describing an Azure service and then contacting the corresponding Azure service in the cloud to do some work. So in the end, the operator takes care for you of the configuration, so simplifying the configuration of your application in one place. It handles installation and upgrade if you change something, handle the security as things like encryption, access control, and network policy, and even scaling if I want to scale up and down my own application. But someone working on Kubernetes already could think about Helm charts for deploying your application, right? Instead of using an operator. Why don't use an Helm charts, or what are the main difference between an operator and using the Helm charts? So for people who don't know, with Helm charts, you have a kind of package manager for Kubernetes. You have a template where you describe your application in a deployment, in a replica set. So you have not custom resource. You have just the Kubernetes built-in resource, right? With a template plus some values in a different files. So in the end, the Helm charts provides to join this information, so your template with the values that you provide, and deploy your application. It of course simplifies to write YAMLs with parameters using templating, because if you need to deploy with different values, you don't need to change your template in the end, but you need to change the values. So the kind of problems that it fixes is about deploy your application with a different configuration in different environments, just changing your values in your values file, but not changing the template. But in the end, the Helm charts helps on the day one operation, which is about deploying your application. The difference with operators is that the operators provide you a way for controlling the entire life cycle of your workload. The operator is not just a package manager, it's a CRD for extending your API server, for having custom resource, plus the controller for watching them and handling them, right? You can simplify to write your custom resource with just one YAML, and the operator will take care of creating the corresponding operands, and it acts for day one and day two operations. So not just deployment, but even upgrades, manage your applications and so on. But of course, an operator is a Kubernetes application. It can be deployed using Helm charts. And in the Helm charts, there is a kind of cool feature which are about making sure that the CRDs for your operator are installed before the operator itself, because if you install your operator but you don't install the CRDs in the Kubernetes cluster, the operator just will raise errors, because when it tries to ask to the API server to watch a custom resource, the API server will not know about this custom resource because you didn't deploy the custom resource definition. So that could be a good way for deploying an operator. And the operator will be configurable using some values or config maps. But how to start? So I want to use an operator. You convinced me, but how to start to do that? As you already mentioned, the operator patterns was born by a CoreOS company, and they deployed and they developed an operator framework. Today CoreOS is part of Red Hat, so Red Hat engineers are working on this. It's a toolkit for handling for developing Kubernetes operator. There is an SDK for writing these operators in Golang, because we know that Golang is the kind of language in the Kubernetes world. But it also provides a so-called operator lifecycle manager for handling operators. We'll see in a bit what it is, but even a registry for providing operators to the OLM, and much more. For people who don't know Golang, there is even a Java operator SDK which is kind of making a lot of progress, mostly in the last year. I have used it for some projects. And you can write in your operators in Java, and it also supports a Quarkus extension. So Quarkus, for people who don't know, is a kind of Kubernetes-oriented Java stack. So you can develop your application in Java, but most oriented for Kubernetes native development. So even building your application, your image in native code, so that you can have faster startup times and things like that. Quarkus has a lot of extensions for everything, for any kind of messaging, HTTP stack, and things like that for writing your complex application. And there is, as I already mentioned, a Quarkus extension for this Java operator SDK. So you can write your operator in the Quarkus way. So these are more or less the best way to start for writing an operator on your own. What's the OLM that I mentioned? It's again an operator for handling operators, because you need somehow a way for installing your operators in your Kubernetes cluster. As I already mentioned, you can do that with the Helm charts, because in the end, an operator is a deployment with some CRDs, and you just do your kubectl, apply, etc., to create your YAMLs and deploying your operator. But there is even this OLM which define a packaging format. It has a catalog and it handles the operator. It means that if the provider of the operator provides a new version of the operator somehow in the catalog, in the registry, then the OLM will take care of doing the upgrade of the operator for the user. OLM is provided out of the box on OpenShift, which is a Kubernetes distribution provided by Red Hat, but so it's possible to install this OLM even on a vanilla Kubernetes installation. So we will see in a little bit during the demo how it works. As I already mentioned, the OLM provides operator installation. There is also this place, which is operatorhub.io, which is a place where most of the Kubernetes operators live. There are a lot of operators. You can see here for Apache Spark, for there is an Akka cluster operator, even Epicurious registry operator, the StreamZ operator that I works on is on operatorhub.io. So you can install your operator and even OLM if you don't have on Kubernetes using some Helm charts. If you want to deploy your operator, you can make it available to the community using this website. So this is the place where you have to search if you want to, if you need to, to have an operator for a specific kind of application. Say that talking about the StreamZ operator, so the Apache Kafka operator. StreamZ is an open source project licensed under the Apache license. It's focusing on running Kafka on Kubernetes, as I already mentioned. So it provides some container images about Kafka and zookeepers and other components. It provides operation for deploying and handling and configuring your Kafka cluster. So it provides a kind of Kubernetes experience for running your Kafka cluster. So not just the Kafka cluster itself, but even for creating users, the topics, and all the other stuff in the Kafka ecosystem, like Kafka Connect, Kafka Mirror Makers, and things like that. StreamZ is, of course, open source, as I already said, is a CNCF sandbox project since September 2019. Let's jump to a demo to see how actually an operator works. In this case, the StreamZ operator for deploying Kafka. So I have my OpenShift cluster. I have the operator hub here. You can see here a lot of operators like the ones that I showed in Operator Hub. I can search for something. I have already installed the StreamZ operator. When I have the StreamZ operator installed, you can see it can handle these different custom resource. So there is a Kafka custom resource, but the StreamZ operator can even deploy Mirror Maker or a Kafka bridge for accessing your Kafka cluster using HTTP, even Kafka Connect, or you can create your Kafka users using a Kafka user resource, a topic using your a Kafka topic resource. So you don't need to use Kafka tooling for creating topics and users and things like that. You are a Kubernetes user, you want to use Kubernetes resources, you want to do everything in the Kubernetes way. So this is how this operator works, even some more complex stuff like rebalance. So rebalance your loads across the cluster. So let's say I have my CloudGen 2021 namespace, and let's say that I want to deploy a Kafka cluster. So I have here a Kafka YAML file, which if we print it, we can see the kind of example that I already showed before on the slides. So this is my YAML describing my Kafka cluster. The name is my cluster, Kafka version, I want 3 brokers, the listener, the configuration, etc. What I have to do is just doing an OC apply -f the Kafka YAML file in the right namespace, so CloudGen-2021. What will happen? The StreamZ operator is watching the Kafka custom resource. It detects that a Kafka resource is created and will start the magic. So if we are going to create this Kafka custom resource, we should see here that, yeah, the first pods are starting up, the Zookeeper pods. So what's going to do the StreamZ operator? From the Kafka custom resource, it creates one stateful set, the my cluster Zookeeper stateful set, with a description about having 3 pods, because we want 3 replicas for Zookeeper. And we can see here that so it has even created the my cluster Kafka stateful set, because I want 3 pods for my Kafka brokers. So it's creating the Kubernetes native resource that I need for running Kafka in place of me, right? So it's not me creating this stateful set. I just created a Kafka custom resource. For example, there will be some specific secrets containing the CA certificate for signing certificates for the encrypted communication across different brokers, but even the client certificate that is used if you want to have mutual authentication. So you want your Kafka client using TLS even for authentication. So you have to sign your certificate with a specific certificate recognized by the Kafka cluster in order to connect to the Kafka brokers. So there are some secrets for handling TLS certificates and so on. There are some config maps created for Kafka and Zookeeper configuration. You can even see these config maps related to the topic operator and user operator, because we can see here that other than the pods for Kafka, there is also this pods, this called cluster entity operator, which is in the end a deployment in this case, because this StreamZ operator deploys 2 more operators handling the Kafka user and the Kafka topic resources. So it's an operator deploying 2 more operators for handling a different custom resource. So it will take care of Kafka resource. These 2 operators will take care of the Kafka user and the Kafka topic resource. And they are just pods inside the, so described by a deployment. So our operator creates everything for us, right? Even in this case, not a PVC, because in my custom resource, you can see that the kind of storage that I defined was ephemeral, so it's just in memory. If you delete pods, the messages are lost, so there is nothing in terms of storage from this point of view. Say that this is the one-day operation, right? But what if I want to do an upgrade on my Kafka cluster? Let's edit my Kafka custom resource, and let's say that I want, for example, change a configuration. So I want to change a configuration like, I don't know, I want to set the auto creation policy. So you can see here that, let's quit here. You can see here that we have this one disabled. So let's just enable the field in the configuration. So let's just say that I want to disable the topics, the auto creation of the topics, because it's enabled by default in a Kafka cluster. So I want to disable. What we want to do is in general, you should change this configuration on each Kafka broker, right? In a normal Kafka deployments. But in this case, what we are going to do is just updating the custom resource, and the operator will check that there is a change, and will start a rolling update of my brokers. So it's going to roll each broker one by one, because for me, so it's not me stopping and restarting the brokers manually, but it's going to change the configuration for the first broker, and when the first broker comes up, then the next one, and so on. So this is the day 2 operation, right? It means that you are changing your Kafka configuration just in one place in your YAML, and you have the operator taking care of this for you and restarting all the 3 brokers one by one for you. But it's not about just configuration. So while this rolling update is running, let's say that I want to scaling up my Kafka cluster. Okay, so in same way as I change the configuration, I can even change here the number of replicas. So I can change everything in my Kafka custom resource. I have the number of replicas here. I can scale from 3 to 5 as I change the configuration, but I couldn't change the listener. So applying a new listener, or for example, changing the plain listener that has the TLS disabled, changing it to as the TLS as enabled, and the operator will just roll the Kafka cluster for me, doing all the stuff. So let's see if the operators ended the first rolling. Yes, the last broker was rolled. So let's try to scaling up my cluster and saying I want 5 Kafka brokers. So saving the custom resource. When scaling up and when scaling down, there is a need for the StreamZ operator right now to rolling the pods first, because some more secrets are created with certificates related to the others Kafka brokers. So it will do first a rolling of your brokers, and then at some point it will start 2 more brokers in this installation, because what it's going to do is going to change the stateful set corresponding to the Kafka brokers, in order to say in this stateful set I want 5 replicas and not 3 anymore. As I already mentioned, you cannot change the stateful set directly to say I want 5 and not 3, because the StreamZ operator will revert back the change, because in your Kafka custom resource you want 3, and it sees that you set 5 in stateful set. They are not matching. The source of truth is your Kafka custom resource. You should always doing the changes on your Kafka custom resource and nothing more, not changing the operands on the other side. So it seems that the last broker was rolled. So at some point we should see 2 more brokers got created by the operator. In the end, it will be the stateful set controller to create 2 more containers, right? So at this point, after the rolling, the StreamZ operator is changing the stateful set. I want to have 5 replicas, and so the stateful set controller is adding the 2 brokers. It will be the same for scaling down, if I want to scale down from 5 to 3. So as you already mentioned in the slides, the operator is still leveraging the other built-in controllers for stateful sets, for deployments, and so on. It's just handling a kind of extra layer, an abstraction layer for your more complex application, which is in this case is Kafka. So let's say that it's everything for the demo. Let's back to the slides. There is nothing more from me. So I really hope that you enjoyed this session. Thank you very much. If you have any question, yeah, you can follow me on Twitter, tagging me on any kind of Twitter, even this the reference to my LinkedIn profile. So if you have any question, don't be scared about asking. You can ask me more about StreamZ Operator, operators on Kubernetes. I will be really happy to share with you my knowledge. So thank you very much for joining, and yeah, see you soon.